Hi, I'm Erin. Today I'm excited to share work with you called Pre-Training in the Lasso. I'll also share its accompanying software called PT Lasso in the R programming language. And before I get going, I want to acknowledge and thank my collaborators on this project named here on my slide. Pre-training is a popular and powerful paradigm in machine learning. In this video, I'll share a method to bring the idea of pre-training from neural networks to sparse linear models. Here's how pre-training works for neural networks. Suppose we have a small data set of images of cats and dogs, and we want to fit a deep neural network to classify them. With pre-training, we start with a neural network that has just been trained using a large corpus of images, say ImageNet, which consists not just of cats and dogs, but hundreds of other image types. Then we fix all of the network weights except for the top layer or layers and train or fine-tune those weights on our data set. This often results in dramatically better performance than the network trained solely on our smaller data set. So why should this work? Well, by training our neural network first with a broad set of images, we learn general features like edges, textures, fur, eyes, and so on. Then, during the fine-tuning stage, we can make use of these features to distinguish between cats and dogs. Here's our motivation. Suppose we have a data set spanning 10 cancers, and we want to fit a lasso logistic regression model to predict 10-year survival. Some cancers have more observations, like breast and lung, and some have fewer, like head and neck. Now, would it be better to pool all of our data and fit one model? Or should we fit a separate model for each cancer? This question is hard to answer in general. Here is our conceptual model of the data. We imagine each row is a different cancer class, maybe the first is breast, the second is lung, and so on, and each column is a block of features. And we suppose that some features are predictive across all classes. Combining all cancer classes and fitting one model would give us the most power to discover these features. We also suppose that some features are predictive in just one or a few classes, and discovering them is easiest when we fit a separate model for each class. Good news, pre-training will give us the best of both worlds. Pre-training happens in 2 steps. In the first step, we fit one model using all of our data, and here we have a chance to discover the features in the first column. And in the second step, we fine-tune this model separately for each class. This gives us a chance to discover the features along the diagonal. Now, pre-training is really a general method to pass information across models. It can be used for group data, like in our example, but it can also be used for data with a multinomial or multi-response outcome, or time series data, or conditional average treatment effect estimation, and so on. Now, before I go into the details of pre-training, I'd like to do a quick review of the lasso. Here is our usual lasso linear regression problem. I want to point out that it's composed of 2 pieces. First, the usual squared error loss, which encourages our predictions, x beta, to be close to our observations, y. And second, a penalty that encourages our coefficients beta to be sparse. This penalty does feature selection. That is, features that are not useful for prediction will be given coefficient 0. Though I showed here a lasso linear regression problem, the lasso can be applied to the entire GLM family, including logistic and Poisson regression, as well as the Cox proportional hazards model. There are many software packages that implement the lasso, and a popular choice, as well as the one we'll use today, is GLMNet in R. Varying the regularization parameter lambda gives us a path of solutions, and an optimal value of lambda is usually chosen by cross-validation. In GLMNet, this can be done with the function cv.glmnet. Now, before I can share our method, here are 2 modeling options that we use. The first is called an offset. This is like adding a column to the data with coefficient 1. In the case of linear regression, using an offset means that we're fitting a residual. We subtract the offset O from our response Y and use our model to fit whatever's left over. The second option is a penalty factor. This allows us to preferentially penalize certain features. Note that when the penalty factor for a feature is 0, the corresponding coefficient is not penalized at all. And at the other extreme, when the penalty factor is infinity, the feature is omitted from the model. Now, both of these options are standard in generalized linear models and in the software package GlimNet. Now we're ready to show how pre-training works. Pre-training happens in 2 steps. In the first step, we fit a lasso penalized model using our complete data set. And in the second step, we fine-tune this model separately for each group. We choose a hyperparameter alpha between 0 and 1, and then we fit a group-specific model using an offset and penalty factor. The offset is a fraction of our prediction from the overall model, and the penalty factor encourages us to use the features that were selected by the overall model. Now note that when alpha is 0, this fits a fine-tuned version of the overall model for each group. The pre-trained models can only use features that were already selected by the overall model, and they must use the full prediction from the overall model as an offset. At the other extreme, when alpha is 1, this approach completely ignores the overall model and just fits a separate model for each group. Now we know how pre-training works, let's look at the corresponding R package. PT Lasso is a package that fits pre-trained models using the GlimNet package in R. It can fit pre-trained lasso, elastic net, and ridge models. Now, one call to PT Lasso fits an overall model, pre-trained class-specific models, and class-specific models for each group without pre-training. The package also includes methods for prediction, plotting, and cross-validation to select alpha. Here's how a typical modeling pipeline looks. We fit models using PT Lasso or cv.pt Lasso. We plot using the function plot, predict with predict, and extract coefficients using coef. Let's go through an example with a simple simulated data set. We'll simulate data with 3 groups and a continuous response. Each group has 200 observations and 80 features, and the 3 groups share 10 informative features, while each group additionally has 10 group-specific informative features. We simulate this data using a helper function in the PT Lasso package called Gaussian example data. Here's a quick check of our data. Our feature matrix X has 600 observations and 80 features, and our response Y is continuous, as expected. Now we're ready to fit a model using PT Lasso. We'll choose the pre-training parameter alpha equals 0.5, though this is really just a random choice for this example. We'll go through 3 steps: model fitting, model prediction, and then extracting the model coefficients. Here's how we call PT Lasso. We pass in our features X, our response Y, our group indicator groups, and a specification for which value of alpha we'd like to use. Now the function PT Lasso uses cv.glimnet to fit 7 models. The first is the overall model, which is one model trained using all 3 groups. Then the 3 pre-trained models, one for each group, and 3 individual models, again one for each group. And a call to plot will display the cross-validation curves for each model. The top row shows the overall model, the middle the pre-trained models, and the bottom the individual models. To make predictions for new data, say X test with group indicators groups test, we simply pass these into our call to predict. And PT Lasso will make predictions for all 7 models. Now by default, it uses lambda.min, the value of the regularization parameter lambda that minimizes the cross-validated mean squared error, for all 7 models. If you'd like to use a different value, you can specify this in your call to predict. If you also provide y-test for model validation, predict will return performance measures. So here we see the mean squared error as well as the r-squared for all of our models. And on the bottom of the slide, we show the support size, that is how many features were selected for each model. Coef returns a list with the coefficients for each of our 7 models. As with predict, it uses lambda.min, but other choices of lambda can be specified. The pre-trained coefficients, for example, will be itself a list of length 3, containing the coefficients for each of the 3 groups. Now, in our example, we chose the parameter alpha randomly, but in practice we recommend making a more thoughtful choice by using either a validation set to measure performance for a few choices of alpha, or cross-validation with cv.ptlasso. Today, I'll show you how to use cv.ptlasso. Cross-validation in the ptlasso package is straightforward. Simply call cv.ptlasso. By default, it will compare 11 values of alpha from 0 to 1 equally spaced apart. And after fitting, it will report the cross-validated performance metrics. So that this fits nicely on our slide, I've hidden the rows for alpha from 0.3 to 0.8. Now at the bottom of the slide, we see the value of alpha that minimized the mean squared error for all three groups, that is alpha equals 0.3, as well as the values of alpha that minimize the mean squared error for each of the three groups. For groups 1 and 2, that's alpha equals 0.4, and for group 3, that's alpha equals 0.3. A call to plot shows us the cross-validated mean squared error as a function of alpha, and draws a vertical line to show the value of alpha that minimizes the cross-validated mean squared error. Now we know how to use ptlasso and how to do cross-validation with cv.ptlasso. But what if we have a data set where we don't know the grouping structure? In our motivating example, each row of X belonged to one cancer class, but we may have, for example, a data set with clinical variables like age and sex, as well as genomic variables. We often have some prior belief that risks are different for different groups stratified by these clinical variables. Well, in this case, we can use the clinical variables to fit a shallow cart tree. Each node of the tree will define a separate group, and then we can just use pre-training as we've already described. Let's go through a quick example. We'll simulate data with three groups and additional clinical variables. In group 1, age will be less than 50, and sex will be equally likely male or female. In group 2, we'll say age is over 50 and sex is male, and in group 3, age is over 50 and sex is female. Here's the code we use to simulate the data and additional clinical variables. I won't spend much time going through it, but if you'd like to look closer, please pause the video or see the R Markdown file that accompanies these slides. Now we train and plot our cart tree using only our clinical variables. Our tree did a great job discovering the groups. There's one group for people under 50, and the people over 50 are split into two groups by sex. We want to use our cart tree to predict which group each observation belongs to, instead of giving us a prediction for the response Y. Here's a little bit of code that modifies the cart predict function to do just that. Now, given our predicted group assignments, we call ptlasso exactly as in our previous example. The only difference here is that we are using predicted groups rather than pre-specified groups. A call to plot shows us that pre-training helps. Now I want to point out here that the overall and individual models are both making use of the group predictions. The overall model uses predicted group as a variable, and the individual models are trained separately for each predicted group. So even in settings where pre-training may not outperform both the overall and individual models, it may yet be the case that identifying a grouping structure in your data will improve your performance. Okay, thank you so much for watching. Now we have all the ingredients we need to use ptlasso with a real data set. Please see below for links to these slides, as well as an R Markdown file that accompanies them. Part 2 of this series will cover more use cases of ptlasso, including data sets with a multinomial target, multi-response data, and time series data. I'll see you there.